Here's a different use of normal distribution in a practical situation. So we have some screws and the radius is normally distributed with a mean of 0.5 cm and standard deviation of 0.2 cm. All screws with a radius of less than 0.44 cm or more than 0.54 cm are regarded as bad screws, okay? If a screw is randomly selected, what's the probability that it's a bad one? So first of all, if this is the mean and this is the standard deviation, then we want to express this and these boundary numbers in terms of the mean and the standard deviation. But we know that 0.44 is actually 3 standard deviations below mean and 0.54 is 2 standard deviations above mean. And so when we put these onto the graphs to identify these three numbers, the sum of these two portions are what we wanted, because these are the bad ones, right? Lower than 0.44, these are the bad ones, and higher than 0.54, and these are the bad ones. So we want these. And the better way to do this is to take 100%, that is the entire area here under the curve, minus this 49.85 and this 47.5. And where do these numbers come from? Well, we just learned that 99.7% of data falls within 3 standard deviations from mean. And this is half of it, right? So that's 99.7 divided by 2. And 95% of data falls within 2 standard deviations from mean. And this is 1/2 of it. So we take 95 divided by 2. The sum of this portion and this portion, this infinite tails, is 100 minus this part and minus this part, which is 2.65%. And so the required probability is 0.0265. Part B. So this time we're not picking one screw, but this time we're picking 3 screws instead. So what's the probability that at least one of these screws is a bad one? There are actually 3 cases: exactly 1 inferior, exactly 2 inferior, or all 3 are inferior. If we have different cases, we could add them all up. But a faster way to do this is taking 1 minus the complement of it, that is, the probability that no screws are inferior. But to say there's no screws that are inferior, that actually involves 3 stages. Not 3 cases, but 3 stages. The first one being the first screw that is good, not inferior. And then the second screw, good, not inferior. And finally, the third one is also good, not inferior. We multiply these 3 stages together, not add them, just like that. And that is actually 1 minus 0.0265 from part A, altogether to the third power, which gives this number here. So part C, here's a very practical situation. The manufacturer produces 600,000 screws, and if the production of each screw has a cost of $0.2, the bad ones are rejected and the good ones will be sold at $0.5 each. Then we want to find the profit of the manufacturer. So when we think about profit, it's revenue minus cost. But revenue of what? Of only selling the good ones, because the inferior ones are rejected, right? But there's a cost. Cost of what? Of all the screws, no matter it's good or inferior. This later part is easy. It's just 600,000 times 0.2. And what about this one? This is the number of good screws times $0.5. And of course, this number of good screws is just an estimation because we're using the probability of the inferior screw. We have to start out with the estimation of the screws that are going to be sold. So we take the total number times 1 minus the bad ones, which is this number here. And so finally, all these numbers are in place. I take this times the selling price minus the total number times the cost, which gives this for the answer.